So, hi Alex. So everyone I'm expecting is here, and let's start up. Okay, so it's just going to be 20 or 30 minutes on some of the maths you do need for the exam, and I'm going to start out with some simple formula rearrangements, so some simple algebra. And before I can do that, really, I need to talk a little bit about multiplication and division of fractions, because I know that some people don't really remember this, partly because you learn it so early in school and you don't use it very much. Okay, so if I'm multiplying two fractions together, so let's say I'm multiplying 3/4 by 4/5. Now, the simple way of multiplying fractions is to multiply the top of the two fractions together and multiply the bottom of the two fractions together. So I can multiply the top of these two and I get 12 on the right hand side. And if I multiply the bottom two together, I get 20. Okay, now that's the answer. Oh, one extra. Hi, Chris.
Hello.
Just starting out with the formula rearrangement, just by making sure people know a couple of basic things about fractions, so multiplication and division of fractions, because that's important that later on when we talk about algebra, because of course some algebra has fractions with fractions just with letters, really. Okay, so we've got 12 over 20. Now, a second step to this process, of course, that most of you will have noticed is that I can reduce that to its lowest, to its simplest form as 3/5. This is equals 3/5. But actually, the important stage I wanted to show you is that we can multiply two fractions simply by multiplying the tops and multiplying the bottoms. Now, the next step of that is dividing fractions. So if I wanted to divide two fractions, so let's take the same fractions, 3/4, and I want to divide by 4/5. Yeah. What I can do is I can flip the right-hand fraction. I can flip this fraction upside down as long as I multiply. Okay, so the reason I think will become more obvious if I split this fraction up, okay, because this is the same as 3/4 divided by, well, I can divide it by 4, and I can separately divide it by 1/5. Yeah. Now, I hope it's fairly obvious that 3/4, that dividing by 4 is the same as multiplying by 1/4. So we've got 3/4 multiplied by 1/4. So dividing by 4 is the same as multiplying by 1/4. And dividing by 1/5, so let's think about a slightly simpler one, dividing by 1/2. I divide something by 1/2. Let's scrub this so I got some space. And I've got, let's say, 7 divided by 1/2. Okay. Now, when I divide a number, what I'm doing is finding out how many of the second number is within the first. So if I divide 12 by 3, I'm looking for how many 3s there are in 12, which would be 4. So in this case, I'm looking for how many halves there are in 7. Well, I know in each one of the 7 there's 2 halves, and so I can immediately see there's going to be twice as many halves as there are whole numbers in 7. And so what I've done to divide by 1/2 is I've multiplied by 2. Okay, so likewise here, to divide by a fifth, well, each one in this bracket here would have 5 fifths in. So if I'm dividing by a fifth and I want to know how many fifths in total, well, each one of them has 5, so I'm going to multiply by 5. So, more consistent color, multiply by 5. Okay. So if I want to resolve that, this is going to be the same as 3/4 times 5/4. So what I've shown here is that that this sum here is the same as this sum. So what I've done is I've changed the divide into a multiply, and I flipped the second fraction upside down. Yeah, and we can always do that with fractions. So if I'm dividing by a fraction, it's the same as multiplying by what we call the inverse of a fraction. Yeah. Now, that has an important special case. If I take 1 divided by, let's say, 4/5, yeah, well, I have already said that I can change that division. You might not think we're doing fractions here, but of course 1 is 1/1. We're dividing a fraction by a fraction. Doesn't really matter as long as the second number, if the second number is a fraction and we're dividing by a fraction, that's the same as 1 multiplied by 5/4, which of course is 5/4. Now, what that means is if I ever divide 1 by any fraction, all I need to do is flip the fraction upside down. Okay, so I can generalize that to 1 divided by a/b equals 1 times b/a equals just b/a. Of course, what that does mean is that if I then do 1 divided by b/a, which of course is going to be a/b. So 1 divided by a number always reverses that. Okay, reverses that process. So we have this this function, effectively, this mathematical generalized equation. 1 divided by anything flips the fraction upside down, and 1 divided by that result will flip the fraction back the other way up. So it's what we call a self-inverse function. I can reverse 1 divided by something by 1 divided by again. Now, this might not seem very useful for now, but later on we will come across this. Maybe not in the in this particular lesson, but in some lessons we will come across this fact. So I'm going to restate that. If I have 1 divided by any number, a/b, the result is b/a. It just flips the fraction upside down. I can also write, of course, I can also write division as a fraction itself. So 1 divided by 1 over a/b equals b/a. Yeah. Any questions about that particular one? It's a slightly oddball function, and it's also a little more useful than it might at first appear, because everything, you can think of everything as a fraction. Most of what we look at will be, in one form or another, a fraction. Yeah. The formulas that you need for all your subjects, I think all but maybe a couple of formulas are just in the form a equals b/c, or something like that. So you've got three different variables, and they're related to each other. Yeah. Now we can rearrange that And things like, for example, 1 over A would then equal C over B. For example, that's just an example of where that might come in handy. Yeah. So do remember that 1 divided by any fraction will just flip the fraction upside down. Okay. Yeah, let's go on to some more generalized formula rearrangements. Okay. If I have an equal sign, and I have a function either side of it. Okay, I'll do a generalized function. In maths, we might say x is some function of x. Don't worry about what it is. The point I'm going to make is that I can do anything to one side as long as I do the same to the other side. Yeah. Except divide by 0. Yeah. There's a few tiny obscure ones which you should not come across. If you do things like some calculations that we do and you try and do them at the pole where they can't be done, then you might get a division by 0, because things like the cosine of 90 is 0. So yeah, there are technically exceptions to this, but you should be kept away from them anyway. I can't imagine you'll actually come across them in any real questions. But if we do anything to one side of the equation, we can do it to the other. Okay, so I can multiply both sides by A. Likewise, I can divide both sides by B. And if I do this, the equal sign remains valid. Now, why is that important? Well, let's have a look at a simple equation first. One we haven't done yet in any of the courses, but V equals IR. So we do electrics. Voltage is current times resistance. Have you seen this? Okay. Now, what if I want to know a calculation for the current? So I want to know I. The trick to rearranging equations is that I want to get the I, or in this case, the I, whatever I want to get on its own. Yeah. So at the moment, I is in the equation, which is what I want, the current, but it's not on its own. So I want to get it on its own. So what I want to do is cancel out anything on that side. And I cancel it out by turning it into 1 if it's multiplied. And you might find 1 or 2 equations where we've got addition. If we've got an addition, we would turn it into 0. Okay, so this is an example where I've got, I think, again, nearly all the equations you're looking at only have multiplication or division in, which actually makes it easier, because then you only need to multiply or divide to get it to equal 1. Okay, so I can divide the right-hand side of this equation by R, as long as I also divide the left-hand side of this equation by R. Yeah. Now, what that means is that the right-hand side becomes I times R divided by R. Well, R divided by R is just 1. And of course, if I multiply I by 1, I just get I. In fact, if you look into really serious maths about numbers, that's literally the definition of 1. It's the number which, when multiplied by something else, doesn't change it, what they call the identity. Okay, so multiplying 1 by anything doesn't change that thing. Okay, multiplying anything by 1 doesn't change it. So what we have here is I equals V divided by R. Now, there is a shortcut for these three-way equations, which most of our equations actually only have 3 elements. And if it only has 3 elements which are multiplied by one another or divided by one another, we can use the triangle method. If anyone's studying at CAT, I don't know if any of you are studying at CAT, don't let Stuart see you do this, because he has some irrational objection to the triangle method. I don't know why. I kind of get his point that you should be able to do formula rearrangement, but the triangle makes it easier. Okay, so we had so what we came out with here, sorry, was we said V equals IR, and I wanted to find I ended up with I equals V divided by R. So that's just going to give myself some space. That's the equation we started with, and this is what we ended up with. Okay. I can do another one. What if I want to find R? Well, if I want to find R, V equals I times R. By the way, if I don't put any, if I put two letters next to each other without anything in between, it's always multiplication. I don't know if you've ever been confused by that. The other one is if I put a dot in between, that also means multiplication. It's just mathematical shorthand. Okay, so if I want R on its own, I have to divide this by I, in which case I get R times 1. But of course, to do that, I need to divide this by I. So I end up with a third equation where R equals V over I. Now, what I can do with the triangle method is to draw a triangle like this with a line across the middle and a multiplication sign on the bottom. And I can then write in the elements here so that the equation is correct. So if the equation I know is V equals IR, I write V on the top and then V equals I times R. Okay, and so this has to be correct if I cover up what I want to find. So now if I cover up V, it says it's I times R. But look, if I cover up I, it says it's V divided by R. Yeah. And if I cover up R, it says it's V divided by I. And you can see that that matches each of these equations. Now, I took that from V equals IR, but I can actually write that. I can fill in this triangle from any of these three elements. If let's choose a different one. Let's choose the speed time distance calculation. Yeah. So the speed time distance calculation is speed equals distance divided by time. And remember, we talked about the fact that you can actually work that out from the units. If you didn't know that, you can look at the units being nautical miles per hour and say, well, that's nautical miles divided by hours, which is distance divided by time. So we can say speed equals distance divided by time. I'll just use S, D, and T for these. Okay, so let's fill in the triangle. Now, so I want distance divided by time, and that equals speed. So now, anytime if I cover up speed, it says it's distance divided by time. If I cover up distance, it's speed multiplied by time, which hopefully you know, distance traveled is speed multiplied by time. And if I want to know the time taken, it's distance divided by speed. And all this comes from that simple rearrangement of formulas where we do the same thing to both sides and it all cancels out. Okay, so let's just scrub this one then. So that works for nearly all the equations you've got to deal with. Now, it is possible that you'll come across an equation with an addition in. So A equals B plus C. So if you had an equation like A equals B plus C and you wanted B on its own, what you've got to do is you've got to cancel out C. Okay. Now with addition, the identity, the way of making it no longer count. Multiplication, we made things no longer count by dividing, yeah, and turning them into one by dividing through. But to make something no longer count in addition, we want to turn it into 0, because if we add 0 to something, then it doesn't change. So what I want to do is I want to subtract C from this to find B. Yeah. So what I want to do on the other side, I'll just have to move that A, so I've got space. I want to subtract C from the other side as well. Okay, so I've got plus C minus C on the right, which is plus 0. And so what I find is that B equals A minus C. Yeah. I'm not going to focus much on this because really that's not anywhere near as important to aviation as the multiplication and division one. Okay. Right. Now, a special case. Okay, so back to the multiplication and division one. It's probably quicker for you to answer the exams if you know a couple of shortcuts. And there are a couple of really useful shortcuts. For a start, okay, let's go back to V equals IR. If I divide the right-hand side by R, let's say I'm trying to find I divide the right-hand side by R, divide the left-hand side by R. That cancels out the R's on the right-hand side because they turn into 1 between them, multiplying by 1. And so we get I equals V over R. Okay, so what is that equivalent to? Well, I've got V equals IR. That's equivalent to taking this R and moving it to the other side as long as I put it on the bottom. So if it was on the top on the right, it has to go on the bottom of the fraction on the left. Yeah. So that's one way of thinking about how this multiplication and division formula rearrangement works. I can move anything across the equal sign as long as it goes from the top to the bottom, or of course I can move this back now. I can move this back as long as it goes onto the top. Yeah, which if we look at the other example we had, we look at the example of speed equals distance divided by time. Well, if I wanted the distance driven, I can move the time to the other side of the equation to get distance on its own. I can move that across as long as I put it on the top on the other side, because it's on the bottom on the right. I can move it straight across to the left as long as I put it on the top, and therefore it's multiplied by speed. So that's the generalized shortcut, and you can always do that. Okay. Now I'm going to use a third example, which is sine. Okay. Everyone knows that sine of an angle called sine theta is opposite over hypotenuse. Yeah, well, I hope you all know that. In fact, we'll talk about that in a minute, and we'll have a quick look at sines and cosines. Now, let's go with the rule I just said. Now, let's say I want to find what the hypotenuse is, and this is a particular shortcut if you want to find what's on the bottom on one side. Yeah, so if you've got a simple equation like this with 3 elements, where 2 of them are division, they're a fraction, and you want to find whatever's on the bottom of the fraction. Okay, well, I just said I can move the hypotenuse to the other side as long as it goes to the top. Yeah, so I've got hypotenuse times sine is the opposite. But at the same time, what I can do is I can move the sine over to the other side as long as it goes on the bottom. And what I've done effectively is I've swapped the sine and the hypotenuse over. And that's a really great shortcut. If you've got an equation of the form A equals B over C, and you want to know C, what you can say is that C equals B divided by A. Yeah, those of you doing radio now in half an hour or so, we'll probably look at that with our C equals F lambda formula. Yeah. Any questions on that little shortcut? Okay. So that's, to be honest, that's it for basic rearranging of equations. As far as I can think, that should do for rearranging all the equations you've got. The most complicated you use really is lift equals CL half rho v squared s. But if you want to know any of the elements on the right, which I suppose are the most complicated, let's say we want to know what CL is, all you have to do is lift. Well, we move everything else from this side. So we have to move all of this over to the other side, but of course it then goes underneath the lift. Yeah, so we end up with CL equals lift over half rho v squared s. Yeah. By the way, if you really want to be advanced, we can go back to our division of fractions, and dividing by a half is the same as multiplying by 2. So if you wanted to do this, you don't have to, you can always put this on the top as a 2. Okay, because if we divided by a half, well, that's exactly the same as multiplying the top of the fraction by 2. Not really necessary, I don't tend to, but if you want, it might be helpful in one or two things. But these shortcuts are generally quite helpful. Okay, so the final little bit I'll go over is trigonometry. Okay, now I personally think that trigonometry is very, very simple, but people are either, I'm not sure whether people are badly taught or they just forget it, because until you come to your ATPLs, you've never used it except in maths classes, probably when you were 14 or 15 years old, and then the GCSE maths exam or whatever equivalent is over in Ireland for anyone over there, anyone from over there. But they're actually a really simple idea. Okay, the trigonometric formulas for values from 0 to 90 degrees, there's a slight change once you go below 90 degrees, are most easily expressed as the ratio between sides of a triangle. So if I take an angle here, and I'll call that angle theta, this side is opposite to the angle. Yeah, so we call it the opposite. Literally it is, it's the side that doesn't touch the angle, it's opposite to on the triangle. Whereas this one's adjacent to the angle, it touches that angle. Adjacent, sorry. And this side is called the hypotenuse just because that's what the Greeks decided to call it. That's just the Greek word for the longest side of a right angle triangle. And this angle here is always a right angle. Now we know that on a flat surface, the three angles to a triangle always add up to 180 degrees. So you can say, by the way, that this must be 90 minus theta, if you want to. But the main important point to realize is that that's got to be a constant angle. So for a given angle theta, this triangle will always be the same shape. There's no choices. It can be bigger or smaller, but all triangles are similar. Now, if I double the size of the triangle, of course, I'm going to double all the lengths, but the ratios of their lengths, the comparison between two lengths will still be the same. And what that means is I can just list a function which is, so sine of theta is going to be the ratio of the opposite to the hypotenuse. Cosine of theta is going to be the ratio of the adjacent to the hypotenuse. And tan of theta is going to be a ratio of the opposite to the adjacent. And that's literally all it means. That's literally up to 90 degrees. That's literally all it means. Any questions so far? And I hope you're all finding this is simpler than you ever felt it was at school, because obviously you're a little older now, understand things a bit better. You're coming back to it, probably never having used it since you were 16 years old and taking some exams, which you probably hated. And now you're coming back to it fresh when you know you're going to need it for a short time at least, and hopefully that's a bit, you're understanding it a bit better. Okay, now just a quick word on when we go beyond 90 degrees, okay, and why these are often called by mathematicians the circular functions, okay. If I draw a circle and a circle of radius 1 unit, Okay, so the hypotenuse, correction, sorry, the radius is 1. I can then draw a triangle with that as the hypotenuse. Yeah. And this length here, which, sorry, I'll draw the angle as well. Here's the angle theta. This length here is the adjacent, but it's also the x value of the coordinates of this point. Yeah. And this angle here is the opposite to the angle, but it's also the y value of the coordinates of this point. And so we can say that sine theta equals opposite over hypotenuse, and cos theta equals adjacent over hypotenuse. We said the hypotenuse is 1. So we can actually say for a circle of radius 1, sine theta equals y and cos theta equals x, because the opposite is y and the adjacent is x. So the xy value of this is cos theta sine theta. Yeah, I am going somewhere with this. Now let's see what happens when we go beyond 90 degrees. If I go to here, that angle is now considerably more than 90 degrees, isn't it? And what I can say is that we end up with a negative value of x. Well, this is x, but it's negative. So what we end up with beyond 90 degrees is, well, cos theta is x, cos has some negative values. Yeah, but from this circular function, we can work out what they are. Obviously, if I then go into above 180 degrees, so if I go way around, you don't need to understand this too well, by the way. I'm just illustrating that sine and cosine actually can have values once you go beyond x and beyond 90 degrees. They have reasonable values, but also how those values behave. Okay. So here in this region, between 180 and 270 degrees, because now this is my theta, they're both negative. X and y are both negative. Yeah, because what we have, this is my y values, this is 0, 0 at the center, and this is my x values. I hope you'll recognize this as this graph thing from school. Okay, so we've got x and y values. And they're both negative to come into this region. Now, of course, what will happen is you can go through a full 360 degrees and then everything starts again. So if I just look at, oh, I've got to share this for you. Let's share this. If I look at the value of sine, it's not the greatest graph ever, but here's the values of sine. From 0, they go, they start out 0, go up to maximum positive, down to 0, go to negative. We said they'd go negative at some point, but then they repeat. Okay, and the source of this repeating is the fact that we go round and round that circle. Okay, so that's the source of the behavior of the sine and the cosine functions. Yeah, is the fact that they're actually circular functions. I don't want to go into it in too much depth because you don't really need to know the detail. It's just that sines of more than 90 degrees or cosines of more than 90 degrees don't make any sense unless you understand that they are these circular functions. And I've gone on a little longer than I intended, but a couple more points, just a couple more points that become relevant in different courses at different times. If I divide sine theta by cosine of theta, I get opposite over hypotenuse divided by adjacent over hypotenuse. Well, if I divide by a fraction, that's the same as actually, let's draw this as a division. That's probably better. I get opposite over hypotenuse divided by adjacent over hypotenuse, which we said, this is one of the reasons I told you how to do division of fractions. We said that's the same as multiplying by the same fraction flipped upside down. So it's the same as multiplying by hypotenuse over adjacent. Well, what we're going to get is our two hypotenuse cancel out. Yeah. And that's going to be opposite over adjacent. Oh, look at that. That's tan theta. I hate the fact that they actually have this. It comes into one equation in instruments. Okay, you end up with a tan theta in one of the equations. The reason you end up you end up with a tan of the, is it, if I remember rightly, it's the tan of the latitude. That's right, because you end up dividing the sine of the latitude by the cosine of the latitude, and you end up with the tan of the latitude in the formula. And this is where it comes from. Yeah. This is something to any mathematician. You mention sine over cos, and they immediately in their heads tan comes up. It's one of the classic identities in maths, that sine divided by cos is always tan. Okay, so that's one thing. The second weird little anomaly that comes up is if I have a very small angle. So let's draw a triangle. I'm going to draw a triangle now with a very small angle. So I don't need straight lines. Very small theta. Okay, and this works well up to 10 degrees. The error is going to be no more than 1.5%. So this works well, certainly even beyond 10 degrees. Okay, so this is small theta. Then my hypotenuse and my adjacent are very similar. This is the opposite. So hypotenuse is approximately equal to my adjacent. Yeah. Now what that means is I've got opposite over hypotenuse and opposite over adjacent. Now it doesn't make much difference whether I use hypotenuse or adjacent, which means these two must be similar. So sine theta is approximately equal to tan theta for small theta. Yeah. Any questions on that? You can also prove that by r sine divided by cos equals tan, but because cos is very close to 1 at small theta. But the easiest way is just to can everyone see that the hypotenuse and adjacent must be very similar here, and that therefore it doesn't matter whether you use the hypotenuse or the adjacent. Yeah. Okay. So that's the main maths you guys need for the exams. Are there any questions before I stop the recording?
No, thank you.
Excellent. Okay. Well, I hope that was useful to you. And those that are doing, we're doing radio nav next.
Anyway. Yeah, radio.